So, hello everyone. Welcome to the second day of Sustainable HEP. I'll give you just a very brief introduction and then we'll get going. So just a reminder of our code of conduct. It hasn't changed. Everybody behaved well yesterday, so keep it this way. For communication channels, you have already seen everything yesterday. Speakers, please remember to upload your slides before the session starts. It's always more practical for people following your talk. We, of course, thank again our sponsors for all the technical aspects of this organization. And just as a very brief recap from yesterday's sessions, we've heard about the science, politics, and ethics of climate change, as well as about how we are doing better, hopefully, when it comes to using gases in high energy physics. And then we heard in two parallel sessions on large scale projects and policy making, as well as sustainable computation. And we'll keep going with compute today, as well as looking into detectors, making them more sustainable. We'll have, during the break, we'll try to take a picture of all participants. So at that time, we'll ask you, if possible, to switch on your camera and we'll just take screenshots. And then we'll have a panel discussing with people that you have here lined up that have worked in high energy physics before, physics or computing mostly, and that made the change to be working now outside of the field, but on sustainability. And so we'll hear about these career changes, how they did it, what they're doing now, and see how it can have an impact also on some of us in the crowd here. If you want to submit questions to the panel, you can already start doing this on this Slido link or from the QR code. But to start the day, we'll have now a presentation by Ben Sheperd. Ben is the group leader of the Magnetics and Radiation Sources Group and chairs the Aztec Sustainable Accelerators Task Force. He has over 20 years of experience designing, building, and testing novel magnetic systems for accelerators, and is passionate about sustainability and is keen to ensure that we build and operate future accelerators in the most efficient way possible. And so today he's going to tell us more about the input from the lab directors group to the European update to the particle physics strategy. So Ben, I'll stop sharing and you can go ahead, and I'll give you a heads up in 45 minutes in case you have already reached that point.
Okay, hopefully everybody can see me and see my slides.
Yes, looks good.
And hear me. Well, thank you very much for inviting me to speak at this conference. So I'm Ben Sheperd from the Accelerator Science and Technology Centre, located at Daresbury Laboratory in the UK. My background is in magnet design, but over the last few years, I've spent a lot of time looking at the environmental impacts of accelerators and how to minimize those impacts. I'm a member of CERN's LDG Sustainability Panel, and today I'll be talking about the work that this panel has done recently. Okay, here's a brief overview. First, I'll introduce you to CERN's LDG Sustainability Panel. We've been working on a report over the last couple of years, which is now published. I'll discuss the principles of life cycle assessment and how they can be applied to accelerator facilities in order to minimize climate impacts, as well as maximizing and highlighting the positive societal benefits of accelerators. I'll go over a few examples of future large facilities. And finally, I'll go over our conclusions and talk about the next steps for our group. Okay, so CERN Council mandated the Lab Directors Group to define and maintain a prioritized accelerator R&D roadmap towards future large-scale facilities for particle physics. The LDG was originally formed in 2021 to report to CERN Council and feed into the particle physics strategy process. It consists of 6 working groups with domain-specific experts in high-field magnets, radio frequency structures, novel acceleration, for instance, laser plasma acceleration, muon colliders, and energy recovery links. In 2024, a working group on sustainability was added. Many research infrastructures around the world make use of accelerators with wide-ranging applications from fundamental physics, material science, drug discovery, and archaeology, as well as more wide-ranging benefits to society. However, the biggest accelerators come with significant environmental impacts. So the Large Hadron Collider sits in a 27-kilometer underground tunnel and consumes as much energy as a small city. Upgrade pathways under investigation call for even larger accelerators to reach the high particle energies required by fundamental physics. This is a source of potential conflict with net zero goals, as we've heard, set by governments and the EU. To retain public acceptance and funding, it's clear that we need to operate our big facilities in the most efficient way, minimizing our environmental impacts. The update of the European Strategy on Particle Physics in 2024 set out the future circular collider as the Plan A particle physics. It also recommended the setting up of detailed strategies for sustainability in large accelerator-based research infrastructures. So the idea behind the working group on sustainability is to produce a set of standards. Our mandate is to develop a set of guidelines and key indicators for the sustainability assessment of future accelerators. This will allow us to make quantitative assessments of the environmental impact of future facilities. That enables comparison between potential options, as well as prioritization of mitigation strategies. We want a flexible and useful set of standards that can apply to a wide range of machines. The working group is made up of 14 experts from a wide range of institutes working on a variety of different future projects, and it's co-chaired by Katerina Bloise from INFN and Maxim Titov from CEA. 2025 update of the European Strategy for Particle Physics was the first to include considerations on the sustainability of future projects. It contained significant contributions from the LDG Sustainability Working Group. The strategy update makes 3 recommendations. Firstly, to carry out detailed life cycle assessment at each stage of new projects. Secondly, we should make every effort to develop and adopt sustainable solutions. And finally, we should strike a balance between in-person and online meetings. For the rest of this talk, I'll be discussing the working group's report on the sustainability assessment of future accelerators. The report was published in September 2025 and revised in March this year. It's published in full on arXiv, and you can access it via this link from my slides, or the QR code shown on your screen. I'll show the QR code again at the end. In this detailed document, we produced an exhaustive set of guidelines to help with environmental assessments of large research facilities. So the assessment of sustainability is based around 3 pillars: society, environment, and economy. A science project can be considered as sustainable if it can achieve its core mission whilst upholding these 3 pillars. It needs a social license to operate, the acceptance and support of the public. It's affordable in the long term with well-managed risks, and it maintains its consumption of natural resources within acceptable limits. The UN's list of Sustainable Development Goals is another useful metric for documenting quantified positive and negative impacts. It's primarily designed to support countries rather than research organizations, but the UN provides a tracker, and CERN's periodic environment report tracks progress against these goals as far as possible. As part of the business case for an accelerator, we recommend a thorough cost-benefit analysis. This can enable transparent sustainability reporting in line with best practices. On the positive side, accelerators deliver benefits far beyond their scientific mission. Firstly, they create fundamental knowledge. Scientific discoveries are a public good, expanding humanity's understanding of nature and providing value to society even when there is no immediate application. They also provide education and training, giving students, engineers, and researchers highly transferable skills that translate into long-term career and economic benefits. Large accelerator projects build international scientific communities, bringing together researchers across countries and generations, creating lasting networks and a continuous flow of scientific output. Through close collaboration with suppliers, they generate industrial spillovers, new technologies, growth products and processes that strengthen industry and stimulate economic growth. Accelerators have also been a major source of open information and computing technologies, producing software, data tools, and digital platforms that are widely used beyond particle physics. They create cultural value through outreach, exhibitions, public engagement, and citizen science, helping to inspire future generations and strengthen public interest in science. Projects can also generate positive environmental impacts, such as biodiversity improvements, habitat restoration, renewable energy initiatives, and waste heat recovery. Finally, accelerators act as engines of innovation, R&D, and international collaboration, driving technological breakthroughs and bringing nations together around shared scientific goals. So, while accelerators advance fundamental physics, they also deliver broad benefits in skills, technology, industry, culture, sustainability, and global cooperation. So how do we quantify environmental impact? The main tool we recommend is life cycle assessment. An LCA looks at the environmental impact of a project across its entire lifetime, rather than focusing only on operational electricity use. It allows us to identify and quantify greenhouse gas emissions, but also a much wider range of impacts such as resource consumption, land use, and pollution. The process has 4 stages. First, we define the goal and scope of the study, exactly what we're assessing and where we draw the boundaries. Second, we build a life cycle inventory, which is essentially a detailed catalogue of all the materials, products, and processes involved. Third, we carry out the life cycle impact assessment, converting those material and energy flows into environmental impacts. And finally, we interpret the results, identifying the major contributors, testing assumptions, and looking for opportunities to reduce impacts. The key point is that an LCA doesn't just tell us how much impact a facility has. It tells us where that impact comes from, allowing sustainability to become part of the design process, rather than an afterthought. The goals of an LCA depend on the stage of the project. In the planning phase, the main objective is to compare different design options and identify the choices with the lowest environmental impact. This is where an LCA has the greatest value because design changes are still relatively easy and inexpensive to make. It also helps demonstrate to funding agencies, governments, and the public that sustainability is being considered from the outset. As the project moves into the engineering phase, the focus shifts towards more detailed decision-making. The assessment can guide choices of technologies, materials, and construction approaches, helping to minimize environmental impacts while still meeting the scientific requirements. In many countries, environmental assessments are also becoming a formal part of the project approval process. So an LCA may be needed to satisfy regulatory requirements and support the case for investment. So the role of an LCA evolves throughout the project lifecycle, first as a tool for optimization, then as a tool for design decisions, and finally as evidence that the project is both scientifically valuable and environmentally responsible. Before carrying out an LCA, we need to define the functional unit. In other words, exactly what system we're assessing. For a commercial product, this is straightforward. It might be a car, a fridge, or even a pair of jeans. But for an accelerator project, it's much more complicated. Typically, the functional unit includes the accelerator itself, the detectors, and the supporting infrastructure needed to operate the facility. The important thing is that the definition is consistent, so that different projects can be compared fairly. That means being clear about several things: which accelerator systems are included, how we treat existing infrastructure that may be reused, whether we're assessing only the initial program or also future upgrades, and how broadly we define the supporting infrastructure, such as buildings, cryogenic plants, data centers, and access roads. Some people have suggested defining the functional unit in terms of scientific output, such as the number of Higgs bosons produced. We argue against relying on that approach because it captures only a small part of a facility's scientific mission and can give a misleading picture of environmental performance. So the recommendation is simple: use a broad, clearly defined functional unit that represents the full accelerator facility and allows meaningful comparison between projects. Once we've defined the functional unit, we need to define the system boundaries, that is, which stages of the life cycle are included in the assessment. We've followed the standard life cycle model used for buildings and other large infrastructure projects. This divides the project into 4 main phases: product, where raw materials and components are manufactured; construction, including transport and installation; use, covering operation and maintenance; and end of life, covering decommissioning and disposal. Depending on where we place the boundaries, we get different types of analysis. A cradle-to-gate assessment considers only material and component production. A cradle-to-grave assessment follows the project through its complete life, including operation and demolition. And a cradle-to-cradle assessment also includes the recycling and reuse of materials. For accelerators, the end-of-life stage is often the most challenging. These facilities frequently outlive their original design lifetime, and major infrastructure is often reused in future projects. So defining sensible system boundaries is essential because it determines exactly which environmental impacts are counted and ensures that comparisons between projects are meaningful. A concept you'll see throughout sustainability reporting is the use of scopes 1, 2, and 3 defined by the Greenhouse Gas Protocol. These help us classify where emissions come from. Scope 1 covers direct emissions from sources under the organization's control. For accelerator facilities, examples include burning fuels for heating or transport, and leakage of greenhouse gases such as refrigerants or SF6. Scope 2 covers indirect emissions from purchased energy, which for most accelerator facilities primarily means grid electricity. This is typically the dominant source of emissions during the operational phase of the facility. Scope 3 covers all other indirect emissions arising from project activities. This includes the embodied carbon in manufactured components and construction materials, as well as business travel, commuting, and other supply chain impacts. For large accelerator projects, Scope 3 emissions during construction can be significant. For future accelerators, there's a common theme. During the construction phase, the main contribution is usually Scope 3 emissions associated with materials and manufacturing. During the operation phase, the dominant contribution is usually Scope 2 emissions from electricity consumption. So understanding these three scopes helps us identify where emissions arise and where mitigation effects will have the greatest impact. Okay, up to now we've talked about measuring environmental impact, but impact means much more than just carbon emissions. An LCA considers several different impact categories, representing different ways in which a project affects the environment. The best known is global warming potential, which measures greenhouse gas emissions in terms of CO2 equivalent. But there are many others, including ozone depletion, eutrophication of water systems, particulate pollution, land use change, water consumption, and resource depletion. These are known as midpoint categories because they measure direct environmental effects. The challenge is that reducing one impact can sometimes increase another. For example, a technology that lowers carbon emissions might require rare materials whose production has other environmental consequences. To deal with that, some LCA methods also calculate endpoint categories, which combine these individual impacts into broader measures, such as effects on human health, ecosystems, and natural resources. Several assessment methods exist, but Recipe 2016 is currently the most widely used approach. As shown in the figure, it links a range of midpoint impact categories to these broader endpoint impacts. The key takeaway is that sustainability isn't just about carbon. A good LCA looks across multiple environmental impacts to avoid simply shifting the burden from one problem to another. After defining the scope and boundaries of the study, the next step is to build the life cycle inventory. The inventory is essentially a detailed model of all the materials, products, and processes that contribute to the facility throughout its lifetime. For an accelerator, that means everything from concrete, steel, and copper, through to specialist materials such as niobium for superconducting RF cavities or rare earth materials for magnets. To do this, we rely on large LCA databases such as EcoInvent and GLAD, which contain environmental impact data for thousands of materials and manufacturing processes. Once the inventory has been assembled, we move to the lifecycle impact assessment. This is where software tools such as Seam Pro, OpenLCA, or One-Click LCA convert all of those material and energy flows into environmental impacts like carbon emissions, resource depletion, and water consumption. Unfortunately, EcoInvent does not have a dedicated category for future particle collider. Our field relies on specialized materials and fabrication processes that are not always well represented in existing databases. As a result, we recommend that the accelerator community develops and shares dedicated environmental data for commonly used components and materials. In summary, the inventory provides the raw data, and the assessment turns that data into quantitative environmental impacts that we can compare, track, and ultimately reduce. The final stage of the process is interpretation, but in practice this happens throughout the LCA, not just at the end. The goal is to understand the results, improve their quality, and identify the biggest opportunities for reducing environmental impact. One tool is sensitivity analysis, where we test how much the results change when we alter assumptions, materials, or design choices. This helps us understand which decisions really matter. We can also perform a hotspot analysis to identify the materials or processes that dominate the environmental footprint. For large accelerator projects, these hotspots are often things like concrete, steel, and major civil engineering works. Contribution analysis looks at which impact categories are most important and during which life cycle phases they occur, helping us avoid focusing on the wrong problem. And benchmarking allows us to compare our results with similar projects and published studies. Finally, we need to assess uncertainty. Every LCA relies on assumptions and incomplete information, especially in the early design stages, so it's important to quantify how confident we are in the results. The key outcome of interpretation is not just a number, it's identifying practical actions that can reduce environmental impacts and improve the sustainability of the project. So, after reviewing the LCA process in detail, the working group's recommendations are quite simple. First, perform LCAs throughout the design process, not just at the end. The earlier sustainability is considered, the greater the opportunity to reduce environmental impact through design choices. Second, use LCAs as a decision-making tool, not simply a reporting exercise. The purpose is to identify hotspots and guide changes that genuinely reduce impact. Third, we need to use common methods, databases, and assumptions across projects. Consistency is essential if we want meaningful comparisons between different accelerator concepts. Fourth, the community should carry out detailed LCAs of widely used accelerator components, such as magnets, RF systems, and vacuum equipment, so that future studies can build on reliable data rather than starting from scratch every time. And finally, we should publish and share environmental data on materials and manufacturing processes, particularly for specialist accelerator technologies where little information currently exists. The overall message is that sustainability assessment should become a standard part of accelerator design, supported by shared tools, shared data, and a common methodology across the international community. Ultimately, the purpose of an LCA is not to produce a report that sits on a shelf, it's to make better decisions. So, how do we apply LCA principles in each phase of an accelerator project? In the next few slides, I'll go through our recommendations. So the construction phase is where we assess all the environmental impacts associated with building the facility, from raw materials right through to installation on site. To do that, we first define a consistent product breakdown structure so that every major system and component is accounted for. We then consider the full supply chain, extraction of raw materials, manufacturing processes, transport, assembly, installation, and even the amount of scrap produced during fabrication. For large accelerator projects, civil engineering is often one of the biggest contributors. Tunnels, caverns, concrete, and steel structures can dominate the construction footprint, which is why these areas receive particular attention in the assessment. A key message is that LCAs should be carried out as early as possible. Early studies are less detailed and less accurate, but they provide the greatest opportunity to reduce impacts through design choices. As the project progresses, the assessments become more precise, but the scope for major changes becomes much smaller. So our guiding principle is simple. If we want sustainability to influence the outcome, we need to embed it into the design process from the very beginning. Once construction is complete, we move into the operation phase, which can last for several decades. This includes not only running the accelerator, but also maintenance, repairs, component replacement, and supporting infrastructure, detectors, and computing systems. For most future accelerators, the dominant environmental impact during operation comes from electricity consumption, making Scope 2 emissions the major contributor. The exact carbon footprint depends strongly on the local electricity mix. A large accelerator can easily consume energy comparable to a town. After only a couple of years running, its operational emissions can rival those from its construction. The largest consumers of electricity are typically the RF systems, magnets, and the extensive cooling infrastructure needed to remove waste heat. Air conditioning and water cooling systems alone can represent a significant fraction of the total power demand. Particle detectors can produce direct emissions using specialized gases, while data centers consume both electricity and water. Maintenance activities and the replacement of components also have an environmental footprint that should be included in assessments. Perhaps the most important message is that operational emissions accumulate year after year. That's why improving energy efficiency is one of the most powerful ways to reduce the overall environmental impact of an accelerator. The final life cycle stage is decommissioning, covering dismantling, transport, waste processing, and disposal of materials at the end of a facility's life. While this sounds straightforward, it's actually one of the most difficult phases to evaluate for accelerator projects. Most industrial facilities are demolished after a few decades. Accelerator physicists tend to have a different definition of end of life. CERN's proton synchrotron is still running after more than 60 years. At DAISY, when HERO was shut down, its magnets didn't become waste. Instead, they were repurposed for the ALPS 2 experiment. In some cases, such as LEP, infrastructure has been reused directly in successor facilities. Activated materials present a challenge. Components exposed to radiation must be surveyed, classified, and handled according to strict regulations. Most accelerator waste falls into the very low level radioactive category, but beam dumps, targets, and other components directly exposed to the beam can reach significantly higher activity levels. The amount of activation depends on factors such as the beam type, operating history, and material composition. Of course, disposal pathways and regulatory limits vary significantly between countries, making it difficult to define a single approach for future projects. Decommissioning should not be treated as an afterthought. Planning for reuse, recycling, and responsible management of activated materials from the beginning can significantly reduce the long-term environmental impact of an accelerator facility. Okay, in this section, I'll look at some planned future collider projects. Our report has tried to make a quantitative comparison between them in terms of environmental impact for construction and operation. I'll start with a Future Circular Collider, or FCCEE, which is currently the leading future collider option in Europe. FCCEE is a proposed 90-kilometer circular electron-positron collider that would be built in the Geneva region and make use of the existing CERN accelerator complex as an injector. The program would run in stages, ramping up to top quark physics at around 365 GeV. Full life cycle assessments have been carried out for the civil engineering works, and more recently extended to include accelerator systems and detectors. The construction footprint is dominated by the large volume of concrete, steel, and other materials required for the tunnel and underground infrastructure. Construction emissions are in the range of roughly 500 to 1,000 kilotons of CO2 equivalent, depending on assumptions about materials and mitigation measures. Importantly, the studies also identified major opportunities for improvement: the use of low-carbon concrete, optimization of tunnel design, and other engineering choices could reduce the construction impact substantially. So FCCEE provides not only a benchmark for future collider physics, but also the most mature example we currently have of how comprehensive sustainability assessments can be integrated into the design of a major accelerator facility. The Chinese Electron-Positron Collider is China's proposed Higgs factory and is conceptually similar to FCCEE. The baseline design is a 100-kilometer circular collider operating at 240 GeV for precision Higgs studies, with the possibility of a later energy upgrade. One key takeaway is that the environmental impact of the operational phase depends strongly on the eventual site. Unlike FCC, the site for CEPC has not yet been selected, and electricity carbon intensity varies enormously across China. Quoted values range from 12 grams of CO2 per kilowatt hour in Qinghai to almost 700 grams per kilowatt hour in Inner Mongolia, leading to very different operational carbon footprints for the same machine. Again, we estimate construction emissions from tunneling alone at roughly 1.1 million tons of CO2 equivalent, making material selection and construction methods critical sustainability factors. The CEPC team has also carried out a number of dedicated sustainability studies, including solar power generation, waste heat recovery, high-efficiency klystrons, improved superconductor and RF systems, and the use of permanent magnets to reduce operational electricity demand. So CEPC is particularly interesting because it demonstrates how strongly a project's sustainability can depend not only on the accelerator design itself, but also on choices about location, energy supply, and supporting infrastructure. The Large Hadron Electron Collider, or LHEC, takes a rather different approach from the other projects we've looked at. Instead of colliding two beams stored in a large ring, the baseline design uses an energy recovery LINAC to accelerate electrons and collide them with the existing LHC proton beam. This would deliver electron-proton collisions at around 1.2 TeV, center of mass energy, while making extensive use of existing CERN infrastructure. From a sustainability perspective, the key feature is the use of energy recovery. After the electrons have been used in collisions, they are decelerated in the same superconducting RF structures, returning most of their energy back to the RF system rather than dumping it as waste. This has a major impact on power consumption. It's a great example of how energy recovery technology can enable high energy accelerators while keeping wall plug power requirements under control. The ERL design keeps power consumption below 100 megawatts. The project therefore serves as an important demonstration of a broader sustainability principle, reducing environmental impact not only through greener electricity or mitigation measures, but by designing the accelerator itself to use energy more efficiently in the first place. For that reason, we highlight ERLs as one of the most promising technologies for improving the sustainability of future accelerator facilities. The ILC and CLIC are the two most mature linear collider proposals and have undergone some of the most comprehensive sustainability assessments of any future accelerator. The ILC is based on superconducting RF technology, while CLIC uses a high-gradient, normal conducting acceleration scheme. A key outcome of these studies is that construction impacts are dominated by materials, particularly concrete, steel, and iron. Detector systems make a surprisingly large contribution because of the large masses of material used in magnet return yokes and calorimeters. The assessments also identified substantial opportunities for improvement, including the use of low-carbon concrete and optimization of tunnel designs. During operation, electricity consumption becomes the dominant contributor, so future gains depend strongly on efficient RF technology and the carbon intensity of the electricity supply. Overall, the ILC and CLIC studies provide some of the best examples of how detailed life cycle assessment can guide the design of future colliders and identify practical routes to reducing environmental impact. The final project we consider is C-Cubed, the Cool Copper Collider. C-Cubed is a linear electron-positron collider concept that aims to achieve collision energies of 250 GeV initially, with a potential upgrade to 550 GeV. Its distinguishing feature is the use of high-gradient, normal-conducting copper RF structures operated at cryogenic temperatures, combining some of the efficiency benefits of superconducting technology with the high accelerating gradients of copper structures. From a sustainability perspective, C-Cubed is the smallest facility we studied, and consequently has the lowest estimated construction footprint. We quote construction-related greenhouse gas emissions of 150 kilotons of CO2 equivalent, significantly lower than the larger collider proposals. The concept is based on achieving very high accelerating gradients, which allows the machine to be considerably shorter than conventional linear colliders, reducing the amount of tunnel construction and the quantity of civil engineering materials directly reduces the embodied carbon associated with the facility. However, as with all future accelerators, operational impacts remain important and depend strongly on electricity consumption and carbon intensity. The project therefore relies heavily on continued advances in RF efficiency and high-performance accelerator technology. So C-Cubed is an interesting example of how innovation in accelerator technology can potentially reduce environmental impact by shrinking the size of the facility itself, rather than relying solely on mitigation measures after the design is complete. Okay, we've looked at how to quantify emissions, but really we want to reduce our impact as far as we can. So what technologies and strategies should we focus on to be most effective? Civil engineering dominates the construction footprint of most future accelerator projects. Large quantities of concrete and steel are needed for tunnels, caverns, shafts, and surface infrastructure. So reducing the impact of these materials offers one of the greatest opportunities for improvement. You need sustainability to start early in the design process. Once a tunnel layout and construction method have been fixed, there is much less opportunity to reduce environmental impact. We can reduce the amount of material required through optimized tunnel designs. Circular tunnel cross-sections are generally more material efficient than rectangular structures, and tunnel boring machines can often produce lower environmental impact than conventional drilling and blasting. Second, use low-carbon construction materials, particularly low-carbon concrete and recycled steel. Low-carbon concrete alone could cut the civil engineering footprint in half. Work with local geology and maximize reuse of excavated material wherever possible, turning what would otherwise be waste into a resource for construction, landscaping, or environmental restoration projects. Use precast concrete manufactured off-site instead of poured-in-place concrete. You can use thinner walls for the same overall strength and have more control over the production. The main point is that sustainability gains in civil engineering don't come from a single breakthrough. They come from a combination of smarter design, better materials, and early planning. Up to this point, we've looked at reducing environmental impacts through design, but we should emphasize that procurement decisions are equally important. Responsible procurement means selecting suppliers and technologies based not only on purchase price, but also on their full life cycle impacts. That includes environmental performance, social responsibility, long-term operating costs, and supply chain risks. We recommend adopting formal environmental, social, and governance principles, following standards such as ISO 2400 for sustainable procurement. This encourages organizations to consider factors such as carbon footprint, resource consumption, ethical supply chains, and circular economy practices when making purchasing decisions. For future accelerators, this could mean requiring suppliers to provide life cycle assessments or environmental product declarations for major components and materials, allowing sustainability performance to be included alongside cost and technical specifications during procurement. The implication is that the cheapest option up front is not always the most sustainable, or even the least expensive over the lifetime of a project. By considering full life cycle costs and impacts, responsible procurement can reduce environmental footprint, improve risk management, support public acceptance, and ultimately deliver better value for society. Once we've reduced impacts through design and procurement, the next step is energy optimization. We recommend following a simple hierarchy: avoid, reduce, then compensate. In other words, we should first avoid unnecessary energy consumption, then improve efficiency wherever possible, and only consider compensation measures for the emissions that remain. This starts with the technical requirements of the machine. Energy use should become a design parameter from the very beginning, following an eco-design approach where different options are evaluated, not just on performance, but also on their lifetime energy consumption. In practice, that can lead to repeated design cycles. Reducing power consumption may require changes to accelerator technology, cooling systems, RF systems, or operational scenarios, but these changes can often produce benefits throughout the lifetime of the facility. We also recommend using official projections for the future carbon intensity of national electricity grids when estimating operational emissions, and accounting for the wider societal cost of carbon through approaches such as shadow pricing. The key message is the cleanest energy unit of energy is the one you never use. Improving energy efficiency not only reduces emissions, but also frees up energy resources that can be used elsewhere in society. One of the most attractive mitigation measures is waste heat recovery. Virtually every watt of electricity we buy eventually ends up as heat. The question is whether we treat that heat as waste or as a resource. The first step is to identify the major heat sources across the facility. These include magnets, RF systems, cryogenic plants, electronics, absorbers, and data centers. We can then map potential local heat users, such as office buildings, industrial facilities, or residential heating networks. The benefits can be substantial. Heat recovery can reduce overall energy consumption, lower greenhouse gas emissions, reduce water use in cooling systems, and create value for local communities through the supply of low-carbon heating. Of course, nothing comes for free. Recovering and distributing heat requires additional infrastructure, such as heat exchangers, pumps, storage systems, and in most cases, upgrades to local heating networks. That's why we recommend carrying out detailed techno-economic studies early in the design process. The bottom line is that waste heat should no longer be seen as waste. If considered from the beginning, it can become a significant sustainability benefit for both the research facility and the surrounding community. The next mitigation strategy is energy recovery. And this is one of the most promising avenues for reducing the power consumption of future accelerators. Normally, after we've accelerated a beam, all of that energy is thrown away. An energy recovery LINAC effectively asks, can we get most of it back before the beam reaches the dump? In an ERL, the beam is sent back through the same superconducting RF cavities with the opposite phase, giving most of its energy back to the RF system before it's discarded. Instead of throwing the energy away, we recycle it. This concept has become practical thanks to major advances in superconducting RF technology. Modern cavities can achieve extremely high quality factors, allowing electromagnetic energy to remain stored in the cavities for long periods with very low losses. Combined with multi-turn ERL designs, this makes energy recovery feasible, even at high beam energies. Here, I mentioned several important examples. The C-beta facility at Cornell has successfully demonstrated a multi-pass ERL, while the Pearl facility is being developed as a dedicated ERL demonstrator. And I've already mentioned the LHEC project, a collider based on ERL technology. The future electron-ion collider plans to use ERL technology for electron cooling and proton beams, showing that the approach has broad applicability across accelerator science. The central message is that sustainability is not only about using greener electricity. Sometimes the biggest gains come from using energy more intelligently. Energy recovery LINACs allow us to retain the performance benefits of high-power beams while dramatically reducing the energy that must be supplied from the grid. While measures such as better materials, heat recovery, and energy recovery can reduce environmental impacts, we argue that the most accelerator-specific sustainability strategy is investment in R&D. Many of the technologies needed for future facilities are still being developed, creating an opportunity to improve both scientific performance and environmental performance at the same time. One important area is RF power generation. RF systems are among the largest consumers of electricity in most accelerators, so improving the efficiency of klystrons and other RF sources can deliver substantial reductions in long-term power consumption. Significant progress has already been made through collaborations between laboratories and industry. Another priority is superconducting RF technology. Higher cavity quality factors reduce cryogenic losses, while new materials and coating technologies can achieve the required performance using less bulk niobium. Both approaches improve the overall efficiency of accelerator operation. Cryogenics itself is another major opportunity. Operating superconducting systems at 4 Kelvin instead of 2 Kelvin can dramatically reduce the power required by cryogenic plants. This is one reason why research into high-temperature superconductors is attracting so much interest. I should also highlight permanent magnets. For fixed field applications, they can eliminate the continuous electrical power consumption associated with conventional electromagnets. Facilities such as ESRF have already demonstrated very large energy savings using this approach, and ongoing research is exploring tunable permanent magnet systems for a wider range of applications. Ultimately, many of the largest sustainability gains will come from technologies that do not yet exist at industrial scale. Investing in accelerator R&D is therefore not just an investment in future science, it's also an investment in making future research infrastructure significantly more sustainable. So I'll conclude with a few key points. The first is that sustainability is no longer an optional extra for future accelerators. It's become a strategic requirement that must be considered alongside scientific performance, cost, and technical feasibility. Future projects will increasingly be expected to demonstrate both scientific excellence and environmental responsibility. Second, we now have a clear framework for assessing environmental impact through life cycle assessment. Looking across the full life cycle from construction and operation through to decommissioning allows us to identify where impacts occur and where mitigation effects can be most effective. The studies reviewed by the Sustainability Working Group show that construction impacts are dominated by civil engineering and materials such as concrete and steel, while operational impacts are dominated by electricity consumption. Fortunately, both areas offer significant opportunities for improvement. We've seen examples ranging from low-carbon construction materials and responsible procurement through to heat recovery, energy recovery LINACs, high-efficiency RF systems, superconducting technologies, and permanent magnets. Sustainability is not about a single solution. It's about making better choices throughout the entire design process. Looking ahead, the Sustainability Working Group will continue to develop common methodologies, improve environmental data sets for accelerator technologies, and support consistent sustainability reporting across future projects. International collaboration will be essential if we want meaningful comparisons and shared progress across the community. And perhaps the most important conclusion is this: sustainability and scientific ambition are not competing objectives. By embedding sustainability into accelerator design from the beginning, we can build research infrastructures that continue to deliver world-leading science while meeting the expectations of society and future generations. Thank you for your attention.
Thank you, Ben, for this very comprehensive talk. Do we have questions? Yes, I see a raised hand. Palestine?
Yeah, thank you, Ben, very much for this interesting talk. In fact, I have one comment and one question. So I will start with a question. How do you comment on the fact that typically life cycle assessment procedures are linked to, let's say, relatively high uncertainty, which is related to the data gaps and the reliance on secondary background data sets? So I'm referring to the database's uncertainty.
Yeah, that's it. Sorry, carry on.
Yeah, so that is the question. And the comment, it is related to the fact that you said you stay against defining a scientific output as a functional unit. And I just wanted to say that I stay against your statement. And yeah, so we are actually addressing this topic. You highlighted on it. So we are talking about large research infrastructures. These are facilities that are delivering science. So it makes, in my perspective, it makes no sense to look solely on the impact part and forgetting the scientific output part. So we need to have, like, to be fair in making our assessment and our evaluation, we need to have like an impression about how the level of the impact is and how the scientific output is. But I do also understand your concern, because even that I am adopting the scientific output when performing sustainability assessment, but I also strongly believe that the addressing of scientific output should be formulated in very careful steps. So we should not give it some special criteria, or we define it in a very limited way. It should be flexible, and the user or the operator who is responsible for performing the assessment should define what kind of output is. So what applies as a scientific output in your own perspective maybe is different than what I see as a scientific output. Maybe you are looking at comparing two different facilities, so your output is different, but maybe I was looking at two different designs and understanding the technologies and making some trade-off comparisons. So my output should be different. So it should be formulated in like a smart way. So that is my comment. And thank you very much.
Okay, thank you. You phrased it as a comment, so I guess I don't particularly need to respond, but I do agree with a lot of your points. I think the issue, I think the main issue that we had with defining it in terms of scientific output is that you end up with absurd figures, like how many tons of CO2 was it to make this facility per Higgs boson produced. And, you know, if I think a Higgs boson sounds like a good functional unit, except that, as you point out, it's the real output is science. You know, it's it's the sort of advancement of understanding of the universe. So in that sense, it's very, very difficult to quantify. You know, if you build a big facility and then you discover a new particle, well, what then is your metric? You know, or should it be, you know, papers produced or something like that? So I guess to make things simple and, you know, enable meaningful comparison between competing projects, we looked at it in terms of like what the functional unit being the accelerator and subsystems. But yeah, I agree with everything you said. It makes a lot of sense. The other question was on uncertainty in the LCA process, and yeah, there's a lot of uncertainty. I've encountered this myself, trying to look into carbon footprints of magnets, and as you know, most rare earth materials come from China, and the level of sustainability reporting that you get is quite variable, to say the least. So you can have like a lump of rare earth material and have a huge variation in the sort of values of CO2 and other factors associated with it. So it's something that really needs to be considered very carefully, particularly for accelerator applications where we rely on very specialist materials and processes, and it's ongoing work. You know, that's why one of our recommendations is to build this kind of centralized database of components and processes.
Thank you, Ben. William, you had a question? You're muted. You are muted, apparently. We cannot hear you.
Oh, sorry. Yes.
Yeah, much better.
Thank you for your very informative and encouraging presentation. I'm pleased to learn the existence of the CERN LDG, hence the value of the sustainable workshop, of course. I will be happy to meet the Sustainable Working Group regarding my ULIS project that I presented yesterday during a more speed dating session. And the ULIS project concerns specifically the large-scale recycling of CERN waste heat, and I think it's a big issue for your sustainable working group. So I hope we will be able to discuss this during the workshop or later, of course. Okay.
Absolutely. I thought I really enjoyed your presentation yesterday, and yeah, it's a key issue. Like I say, we use a huge amount of electricity, and it all turns into heat eventually. So if we can make use of that instead of just bumping it into the atmosphere, then even better.
Mm-hmm. I have just a little question. Just about your slide about the forecast of 1 to maximum 2 terawatt-hours electricity for the FCC, but I've read in some reports that they speak about more of 4 terawatt-hours. I think is it just because this 4 terawatt-hours? It means also inclusive all the pre-accelerators like the PS, SPS, and so forth. The whole complex of CERN, I suppose.
Yeah, I don't have a handle on that, how that number was produced. Sorry.
Actually, I think I know that the 4 terawatt-hours is for FCC HH, so very remote in the future. We have no clue if it will happen.
Yes, sorry, you're absolutely right.
FCCEE, it's more like 1.3 or 1.4 terawatt hour on average over different energy cycles that range from 1.2 to 1.8 terawatt hour per year, depending on the energy of the collisions.
But in any case, it's a lot of potential heat that we can recover. Maybe recycling in neighbors in Geneva or France of the accelerator, of course.
And I suspect that's where Ulysse can become interesting, because the problem is that we run in the spring and summer, while we need the heat in the winter.
Yes, and that is the big question that is for all the problems for energy. That is, we need build a very strong seasonal heat storage, electricity, but also heat, of course, because if we see about 50% of our energy is just for heating purposes. If we see very globally, of course. Okay, in any thanks for your presentation.
Thank you. Thanks, Jan, for saving me there. I remember that. I remember that number about FCCE now.
So thank you very much, Ben. I see no more raised hands, so that's perfect, because that means we're right on time and we can start the second part of the Sustainable Computation submitted talks. And so our first speaker is Natalia Szczepanek. Are you connected? Hello. Yes, you're here.
Yeah.
So please go ahead and share your slides.
Sure.
And I'll give you a 12-minute warning just in case.
Okay. Can you see my slides?
Yes.
Perfect. Okay, so hi everyone. It's very nice to be here. I'm working at CERN, and today I would like to tell you about the work we are doing in the context of benchmarking working group. And my presentation is towards unified power and efficiency monitoring across the worldwide LHC computing grid. So let's start from discussing shortly something that we are now all well aware, but I think in the context of WLCG, it's important to say about it even a bit more. So why is sustainability so important in WLCG? Well, we are operating on around 200 sites across 42 countries, and 80% of the computing power sits outside of CERN. Daily, we are using almost 1.5 million CPU cores across entire WLCG. And with incoming Halloumi era, the computing needs will increase. From looking at the optimistic scenario, it can be around 40% higher than in run 3, but looking at pessimistic, it can be even 5 times higher. So we should better understand the power consumption and energy needs that WLCG needs to make better data-driven decisions. And where are we right now? We are in WLCG, there are 3 environmental recommendations guiding the community, which the first one is focused on measuring and monitoring. The second one is all about the efficient hardware, and the third one about the sustainability plan. So all of that is guided by the 4 M's, which stands for measure, model, monitor, and moderate. And in this talk, I will focus mostly on the 3 first M's: measure, model, and monitor. So the problem that there are a few problems that I want to touch during this presentation. First is that there is no standardized power monitoring across WLCG sites. The second is the value 10 watt per core, which shows from time to time in some presentation that is being used as, let's say, the standard. The third one is that the vendor TDP is not equal to real power under high energy physics workloads. We don't know PUE for given site, so it is even more difficult for us to estimate in the right way the final power, and there is no common method to estimate carbon from grid jobs. And in this presentation, I want to present you two methodologies. First part of the presentation will focus on the power measurements that we successfully collected from a number of sites on WLCG. And the second part will be related with TDP analysis. So what we can do with the numbers to actually make them have a real value in terms of entire WLCG. Later, I will show you some results, and also we'll talk about the impact that we can that it gives. So let's start from the power measurements. When I talk about the power measurements that we are collecting, we are using the infrastructure that we are continuously developing in the context of benchmarking working group. The infrastructure that I'm talking about and using mostly is the HEP benchmark suite, which is an orchestrator of multiple benchmarks. And the suite allows us also to collect several plugins. Like CPU frequency, load, and power consumption. At the end, we have very nice time series that we can analyze and use to our analysis. And we can measure the performance under different conditions. Standard use of a standard way of measuring performance is while we are doing it in an isolated environment. So we have the entire node to use, and in this case, we can also define later the pledges of our resources. And the second one is the real-world conditions. So instead of benchmarking an entire server, we are using a batch system and the jobs to collect performance informations as well as other plugins that are available. So in this talk, I will focus on the real-world conditions. So when we are sending the jobs to the grid and we are collecting information from there. As I mentioned, we are leveraging existing submission infrastructure, and when we are landing on a given site, then everything is landing in our database, so we are able to do our analysis. And since more than 1 year, we collected more than 70,000 measurements that include power consumption. Because without power consumption, we collected much more information, but that was the missing part, which last year we presented a way how to collect this information without any privileges issues that can concern site admins, which you can have a look at possible collectors that we proposed in our repository. So going to the measurements and the results from those runs. So what you can see here are two plots. One is from AMD, the second one is from ARM. This is the plot which represents the power versus load per core. You can see here the scatters, and one scatter means that we landed at the machine at a given node, and then we performed the benchmarking on those 8 cores, and at the end we have aggregated value from entire time series for power and also from load, and we can then visualize it in this way. So what we can read from that is that we have a clear trend that shows a saturating trend with load around 1 for x86 architecture, but for ARM it is exactly the same, but we didn't collect the information for the load more than 1. We need to differentiate the noise and outliers from deliberate server configurations. And for example, in here, based on this plot itself, you can already detect some anomalies, which can be either deliberate choices made by site admins or some misconfiguration, which we proved in the past that we can we can detect that successfully. And thanks to those plots, we can later, looking ahead, provide dynamic power prediction, which in the moment is provided as a proof of concept. But what it gives us a possibility to, looking at the load of machine, predict what is the power consumption and better estimate the carbon footprint from those jobs without any static values. And now let's focus on the second part of the analysis, so TDP and power analysis. Why? Because as you can see with the measurements that I just presented, there is one thing that we need to consider, that we need to have access in some way to those computing resources and to those sites. It might be very difficult to land on entire WLCG, and the question is what we can do if we don't have access to all of those nodes. Well, the TDP information is available through different vendor specification websites and public databases. So we can collect the TDP information and then from the measurements that I showed in the first part, derive scaling factors that allow us to apply them and know what is the predicted power consumption for a given server. And then if we know what kind of resources are being used at a given site, we can determine usage weight for those resources. And by calculating it all together, we can derive value per power per core per site, and later also the final value for entire WLCG. So let's look one by one what we did. So first of all, looking at the median server power and information about the TDP, we can derive those scaling factors. In this case, it's 1.34 that we apply later to our TDP to scale it to the power consumption. From where we have the information, we collected the information from vendor, from official data sources to have them ready to query. We provided the data table. For the moment, it's also proof of concept is available, but the plan is to be extended in the future. So we have we have a source that we can take those information. And at the very end, we can answer the question, what is the estimated power per core of some WLCG sites? So here you can see estimated power per core for anonymized sites. The value that is being used, 10 watt, seems to be overestimated because if we take the average PUE that is available in the literature, it seems that after our measurements, the estimated weighted power per core is around 7.2. So we are doing better for around 30% comparing to what is being said in different sources. So at the end, with those information, we can also develop something like site energy calculator and give it to site admins, so they are able, even without direct power measurements, to check what is their power consumption of entire data center of a given cluster. So to summarize, we leverage existing benchmarking and job submission infrastructure to collect those power measurements, and together with publicly available TDP information, we were able to provide an estimate for WLCG power per core, which seems to be lower for about 30% than what what we thought it is, using the PUE of 1.45. Well, our next steps are to provide automated reports for site admins that, for example, allow them to get information about the anomalies quickly and extend those studies even further. So thank you very much for listening.
Thank you, Natalia. Do we have questions for Natalia? Yes, Anna, please go ahead.
I have a quick question. So I think this is really great work, a really nice outcome. And I guess looking at it from taking a step back, how are you communicating this to users, and how can users potentially use and understand this output to then try and reduce their impact? Is that something that you're looking into at all?
So we are in this particular work, we are focusing on providing the estimates for a WLCG, but of course our work is not just about that. We are also looking at different configurations that are optimizing the power usage. It was not presented in this presentation, but we as well are looking into that, and there will be proceedings that we will also provide in the near future about those aspects as well, like playing with the frequency or the governors or others.
Brilliant. Okay, thank you.
Just a very quick one then. I've heard in the past that people, for instance, in collaborations on the WLCG have tried to give average numbers all the time and not site-specific numbers. So there is no shaming or whatever, because computing centers do not always have the choice of doing whatever they are doing. They are also located in a specific area where the electric mix is not their choice either. How do you see this evolving, like making recommendations to sites about whether they should exist or not, or what they should procure? Or...
I think it should never be about, let's say, the blame game. We are all working in the same direction and of course we shouldn't blame at the given country, right, and the given data center in a given country just because they are using different I don't know, energy power. But I think it's very important to do this kind of studies to understand better what we actually can do and what is possible, to provide better recommendations, because maybe some recommendations work for one data center, don't work for the other, but without prior understanding of what power consumption, what energy looks like in a given place, we don't really know what to do.
Okay, very good. Thank you very much, Natalia.
Thank you.
And we move to our next speaker, Federico Ronchetti, who's going to talk about GPU usage at Alice.
Hello, thanks. I'm sharing the slides. Hopefully you can see them.
Yes, they are not in full screen though. Yes, there you go.
Sorry, I was not in the first one. Okay. So thank you for the opportunity to speak on behalf of myself and also my colleague Giada, who helped me with these slides. So I will talk about the EPN farm of the Alice experiment. This is a GPU farm that features some efficiency aspects. So just to recap the context, we have been just finishing round 3 and Alice was upgraded for round 3. This means that we could run at 50 kHz hadronic interaction rate, which has to be compared with the 8 kHz of round 1 and 2. This thanks to the detector readout upgrade. Basically, we moved from multi-wire proportional chambers for the TPC into gems and to monolithic pixel sensors from hybrid pixel sensors for the inner tracker. And with this upgrade, we were able to also run continuously because we went from a trigger readout to a continuous readout. To do that, we had to deploy a new software model and new hardware, of course, for our online farms, since we wanted to do basically physics online. So this is quite specific to Alice. So our farm can calibrate the data and produce tracks online. So what gets stored in a compressed format is already the first pass calibration. It's not yet to be used for analysis, but it's the first pass. So we have 350 nodes and 2,800 GPUs of AMD Instinct MI100 and MI50 generation. And with that, we managed to collect basically 7 inverse nanoburn-in lead 4 and 3. And now we look forward for 4 and 4. So 4 and 4, we also will have minor upgrades. The big upgrade for us was already done. But we will have minor upgrades and we will need also a new farm. I will say something on that. So how does the continuous readout work? Basically, you can imagine it like a long exposure picture. The time of exposure is a multiple of the LHC orbits, and we can tune it to a number that can be up to 256. We chose 32 for technical reasons, because the time frame then becomes too big and the grid sites cannot process it. So what this farm does, basically we have this stream of time frames that are sent from the readout into the farm. The compute of the farm is 99% dedicated to the TPC tracking because the TPC has to record very high multiplicities in lead. And the calibrations are run in a few dedicated CPU-only nodes. And we also then do actually an entropy coding of the time frames. So we don't store the raw time frames. This is unfeasible because it's a huge quantity of data. So we throw them away after compression. So that's quite, let's say, bold. Yeah, and another important thing is that the grid code and the sync code and the online code are exactly the same. So as I said, this is basically a must for the data taking of Alice because there is no way to take data without this farm. So this just shows a bit the data flow and the hardware that supports it. So you see here the Alice detector. We have the central timing processor. So we don't do free running. We do continuous readout. So we need still a timing, but this is not a trigger. It's just a clock. So with the fibers, we get into the FPGA cards that reads out the detectors. There is a small farm that basically it's a readout farm. So it basically just does zero suppression and a few other small local processing and then sends the data over InfiniBand into our farm, into the EPN farm. In lead, this data transfer can be up to 700 gigabytes per second, and happens over RDMA. In the EPN farm, there is the event building, and then the data are sent to the EOS instance in CERN. We have a small instance of EOS at 0.2 since we could be cut out from Meren, so we have let's say a small buffer, and then from Meren the data goes to the grid tier 0 and tier 1. Yeah, and this is the infrastructure of the farm, which I will also discuss. So one efficient way to move data is to use RDMA and low latency network. This we do with an InfiniBand network from the readout farm, where the machines are connected to detectors. So the time frames we call them sub-time frames because you just see a slice of a detector. So you see the same time, but as a different slice in space. And then they get some ID and they get transferred to the EPN farm directly in the memory. And then each node starts to process timeframes with the same ID. So it's a simple round-robin scheduling, but it's quite efficient. This is how a node looks like. We have 8 GPUs in a 4U node. The node has 2 NUMA domains, so it's kind of, sorry, this is my touchpad. It's kind of like having two servers. So the important thing here is to note that one GPU can basically do the job of 80 ROM CPU cores in synchronous. And it can do in asynchronous the job of roughly 55 cores. This farm exhibits like 43 petaflop in vector single precision operation, which is what we want because our tracking just use single precision. And if you do some arithmetics, you can see that you would have needed a much bigger farm, like 2,000 servers instead of 350, if you want to do this with CPUs. So this is quite, let's say, efficient because CPU consume more power, they run at higher frequency, and they have less cores. Okay, so the synchronous reconstruction, as I mentioned before, you can see the schema here on the right. So basically, there is some local processing done in the readout farm, but it's very minimal. Most of the game happens in the EPN farm, so it uses GPU processing. So the solid green, dark green is what happens in the reconstruction, either in sync or async. So that task in green, it will always run in both scenarios. Then there are the light green tasks, which run only in sync, and they use a few % of the events in sync. And then the shaded tasks that they run only in sync. And of course, all this is piloted, is managed by the AliCS, which is our experiment control software. And as I mentioned, then there is the entropy coder that writes out the coded CTF and compressed. For the async part, it's basically done on all the events with the full calibration passes, so and repassing on the same calibration with using the previous step as feed. Of course, again, there is no more experiment control because this doesn't run online, but there is still the access to the condition database. And the asynchronous processing basically then stores the analysis data objects on the grid. Just note that the EPN farm can be a grid node. So actually, it's quite a big grid node. It's like 17% of the Alice grid. And it's the only grid node that can process LED events because of the size of the timeframes. So it's quite relevant also in async. And the allocation of the resources between sync and async is done according to the operational conditions. I will say something more for the orchestration part. I want to say a couple of things on the infrastructure because all this is hosted at Alice Point 2 in this modular container structure that uses an adiabatic cooling system. So our PUE is quite good. Especially when we run in sync. When we run in async, it may be less good because async goes in batches, so there may be a moment where there's no, let's say, CPU utilization or not as much as we would like. And this is also a reason why we want to improve our orchestration to keep the farm busier. So that's a summary slide that shows the synchronous processing that happened. This is from 2024 because this was one of the runs or the periods of data taking where we could run at 50 kHz full blast. We then have been running at a lower rate because of some TPC or some issues in our tracking detector, but this has nothing to do with our farm. So when the detector was running at 50 kHz, we could digest all the data, as you can see from the plots on the left side. You can see the time frame buffer utilization per node and the input time frame data rate per node. And here nicely, the output of time frames that follows the luminosity. You see the leveling at 50 kHz and then the natural decay of the field. Those are two summary plots from run 3, the integrated luminosity recorded for proton-proton and for lead-lead. So as you said, it's roughly 7 inverse nanoband, which is what we wanted. And we got much more PP. Coming to the orchestration, as I mentioned, we have different mode of operations: async, sync, and then we also share. Sometimes this they can coexist. So all this, of course, requires some orchestration, and then there is also the orchestration in the data taking itself, which has a huge impact. So we have some, let's say, in the current setup, we have some in-house components like this EPN process orchestrator in the EPN farm, or this EPN control system, which talks to the experiment control system. And on the readout farm, you also have, these are not in-house, but they are like a bit of abandonware, like Apache Mesos and so on. So the idea would be to move to Kubernetes to integrate more these two farms, or at least tie them better, and also be more able to exploit the farm dynamically when we have to switch from sync to async. So imagine you diminish the interaction rate, so you don't need more. You need less nodes in synchronous. You can automatically free these nodes to go in async. Okay, I think I'm done. So I'm just saying that we are also considering new technologies for the upgrade of the farm for RAM4. So we are testing new GPUs. And okay, I think the summary is not really important. I said all I want to say.
Thank you, Federico. Do we have questions? Yes, Christine has a question.
Yeah, I was a bit curious if you could be a bit more specific on the links with the sustainability. I assume now this is a very optimized system, so compared to the old system, you save a lot of energy. Is this the case, or can you specify this a little bit more in depth or quantitatively?
I think, yeah, I mean, so the figure I like more is this comparison with the a CPU farm. I think this says a lot. It's quite sustainable to run GPUs. Of course, to do that, you have to invest in software. So because you need to run the same software on CPUs and GPUs if you want to do what we are doing. And this for us was a big effort, but we would consume twice as much energy, and we will have a much bigger farm if we wouldn't do this. So this is one of the key aspects. Then you can also see the fact that the adiabatic cooling is quite efficient. Of course, we bought this farm already 6 years ago, so now we may have done different choices directly with cooling, but at the time with air cooling, this was one of the most efficient. And we also produce our own purified water without any chemicals. So we just use reverse osmosis. So I think this is a nice example of sustainable computing, even though it's not ultimate, of course. It can be improved.
Thank you. Shreyasi, you have a question?
Hello. Yeah, thank you for the nice summary on the of the working system in Alice. So I just had a question on your outlook of Run4. So the one before conclusions, you say that in Run4 you will still try to optimize the GPUs. I just want so yes. So do you when you try to select which one is the best, do you also take into consideration only the efficiency of the GPUs, or also, I mean, the working performance, or also the energy efficiency and everything is taken into account while making the purchase, final purchase and everything?
Yes. So yes and no, in the sense that yes, if we would have an infinite budget, but as you know, the prices of GPUs are exploding, and also the prices of memories. So we are still trying to find the best, let's say, compromise. What we want to do is, of course, to use less GPUs, because our GPUs are simply obsolete now. So there's no way we can run with these GPUs up to the end of run 4, because first, they die much quicker than CPUs because of just thermal stress. And second, we don't have spares. I mean, we have some, but we cannot, not enough. So we would need to switch to another, to a newer generation. So the idea is this would already grant some improvement in the efficiency, because with the current generation, for instance, of NVIDIA, one GPU of Blackwell at 600 watt can replace almost like 6 of our GPUs. So basically, if we put one card in one server, we already have the equivalent of the old server. So that would reduce either the cost of the size of the farm of quite a factor. It would be less than half. And yeah, but it's premature to give you a final answer because we are really in the exploratory phase.
Yeah, but thank you very much. That answers the question very well. Thank you.
Okay, thank you, Federico.
Thank you.
We will move on to the next talk by Andreas Ralph Redelbach. Yes, are you?
Yes, let me share. So are the slides visible?
Yes, all good.
Okay, thank you. So yeah, I will give an overview of some measures towards also increasing sustainability in the communities of research on universal matter. Explain a bit more how this is related to this ERUM data hub and communities. So first we'll introduce some of the main goals as defined in the white paper basically 2 years ago, and also introduce our action group, which is now also set up. Then come to some of the results, small subset of them, and show some recent developments for improved teaching and outreach in sustainability. To give you a bit of a chronological overview, so basically the whole project started in a workshop 2023. Let's link here. And this was then the basis for defining the goals as a white paper in 2024 to really summarize all items and all goals and the whole context we had been discussing the year before. And this was followed up by some short extra events, which you can also refer to by this link. And then we had a major second workshop last year, where in addition to sustainability, also ethical aspects have been addressed and taken into account. And directly after this workshop last year, we then had basically formed what we call ERUM Action Group. We'll show this also a bit more as a picture coming slide. And kind of the last step in this project up to now officially has been the review on the progress made up to beginning of this year. So now ERUM communities, I mean, this is basically the summaries of all of the related sub-communities. So fundamental research on particle physics, astroparticle physics, astronomy, and all of the technologies behind these fundamental questions. So in principle, these 8 sub-communities, so the project as such is located in Germany, but of course all of these sub-communities and also facilities are internationally embedded, so it's also internationally relevant. The starting point is basically Germany. For this white paper, coming back to these goals, and also, I mean, of course, we cannot go through all of these goals, and many of them are also addressed, maybe even almost all at some extent in this workshop. So I mean, we structured them by short time scale goals, medium time scale, and long time scale goal. And I will pick up, basically focus on one for each of these classes. So the monitoring and reporting of energy consumption at shop level will be addressed for the short time scale. Then we had various also for medium time scale, for example, for fair verification of software and data. But I will basically focus on designing software for optimized energy consumption and providing tools to measure it in this talk. And coming to the long-term goals, here, I mean, they are the most challenging ones, of course, and need to be coordinated with other partners and in larger context. So mainly here we will have an update on adjusting computing in so-called nearby available computing centers and renewable energy. And all these goals can, of course, as I said, already be found in the corresponding reference publication of the white paper. Well, so after the second workshop and white paper, we really formed our action group, which has a strong focus on this sustainability aspects in digital transformation. So really raising the awareness even more within communities and also really focusing on creating and curating communication at different levels. I will show also 2 examples in the final slides. So really, yeah, having an impact, and last but not least, also providing training material on sustainable computing. So as for a short-term goal, the monitoring and reporting of energy consumption at shop level, I mean, this is now becoming more widespread, as most of you will already know. I mean, just mentioning example of DESI. So here they already provide an estimate of carbon footprints of batch jobs to individual users, or a small-scale cluster, the WISPA cluster in Aachen. Here they also include indications when the energy mix is most favorable for running the jobs, so not only the CO2 footprint, but also some indication for optimizations. And at large scale, of course, yeah, one can mention, for example, the Atlas experiment, where a recent publication also highlighted, yeah, the availability of estimates for carbon footprints for individual tasks. And I mean, this is of course also then linked to more information about the calculations and really useful development. For midterm goals, so designing software for optimized energy consumption and other related tools, of course, they are very relevant, and there are many examples. Just, I mean, in principle, they combine more efficient computing languages and optimized data formats. For example, one nice example can be the awkward arrays, which are based on teachers' memory allocations. And so this really simplifies parallel processing instead of event-by-event calculations. And for many users, the RN tuple format in root is really helpful in directly implementing thread safety and, yeah, performance gains as compared to the traditional tree formats. So, I mean, in principle, many tools exist to measure energy consumption at software level, but of course, they are not yet that widespread, as for example, testing setups. So also related to this medium scale approaches and goals, I mean, one can also practically try to use a set of well-established and efficient software components to maximize the benefits and efficiencies for many users at the same time. and educate scientists. Yeah, this is of course also very relevant to minimize future resource usages in computations. And one very critical point we also had mentioned back then, I mean, getting energy certifications of software programs. And this is probably on a longest scale very relevant to really document these efficiencies and also get the attention in different project planning phases, sustainability aspects of software. Just pointing towards two nice examples. So, for example, for a really huge collection of efficient computing tasks, tools, and training, which have been verified by experts. Maybe some of you already know the so-called RSQ kit, Research Software Quality Toolkit. So please have a look. I think this can be useful for many of you. And we also recently learned from Jeremy Cohen that there is already the cross-domain certification model in the UK, which is being built. And please have also a look. This is also a very nice development. For the long-term goals, so adjusting the computing according to the availability of renewable energy, in particular close to offshore wind parks, or basically using only renewable energy as much as possible. I mean, of course, this is really challenging. And as far as we know, there's not much support yet, maybe in the longer term. But anyway, we established one project, which is directly related also to aero data, called Sustainable. I mean, this project just started beginning of this year, and it really aims at including availability of green energy in an automated job scheduling system. So I think it's a really nice project, can be prototype for others hopefully. Then two examples for our outreach and teaching projects. So recently we had a first episode as a podcast. So it had a focus on artificial intelligence and its relations to sustainability, quite large context. And yeah, please just, if you find time, also follow this link. I mean, we will also have more podcasts, also with more focus on large-scale scientific infrastructures and future approaches. And finally, this is really just a really quite new slide and approach. So here you can see the corresponding QR code, which directly points you to our slide deck. So a really nicely developed set of slides to motivate individual research group who may not have had that strong focus on sustainability yet. So we offer some practical starting points for small step contributions, and also offer it to present it in interested working groups. So please have a look. So summary, I mean, as such, this project in Aerom Data for Sustainability is cross-disciplinary, so really not focusing on one single community, but many, which are related, of course, to some extent in fundamental physics. There is some progress, as you all know already, but we also try to really review this recently in our paper. We developed this multi-step framework for integrating sustainability into everyday research practices, and we really look forward to broadening the use cases we had so far towards more global efforts in sustainability. So yeah, please reach out to us and links, contacts. Thanks for your attention.
Thank you, Andreas. Are there any questions, Andreas? So I have one. You mentioned an approach of using the surplus renewable energy to run the computing farm, which of course is an interesting idea, but if you are not running it when you don't have this surplus, and that means your farm is not running at 100%, which is also coming with environmental costs, right?
Yeah, I mean there is some trade-off, and yeah, I mean of course there can be some sweet spots which we also want to identify. I mean, of course, renewable energy typically comes in kind of yeah, some cycles and at some frequencies per day and or triggered by weather, and so it's, I mean, there is some dynamic range, and it's, yeah, we really try to combine some predictions and model this in the logic of the system. But yeah, I mean, of course, it must be combined with other traditional data centers in practice. So relying only on this approach probably not be the very efficient
Okay,
one.
thanks. Manuel, you had a question?
Yes, thank you. I have a question. You mentioned in slide 10 about a library that is awkward arrays. And this sounds like a library that can be used not only in high energy physics, but outside in the field. And has it been used outside it or not? Or
I'm not completely sure. I mean, yeah, I mean, as you said, it was developed in the context of high energy, but it is really generic, and I think there really should be examples. Maybe you can write this also as a comment or question in the MetaMost channel. I'm quite sure we can find nice example for awkward also beyond the original development.
okay, thank you.
Right. Thank you very much, Andreas. And we will switch gear now, moving to RPCs at CMS with a talk from Joao Pinheiro. So
Hello,
we'll get...
everybody.
Hi.
Hi, can you hear me?
Yes, very well.
Great. So I will share. Can I share my slides?
Yes, please.
Okay. I hope you can see them, and now in full screen mode.
Yes, you can go ahead.
Okay, thank you. So first of all, thanks a lot for the opportunity. I am João Pinheiro. I'm from Rio de Janeiro State University, and I will speak on behalf of the CMS Muon group on the strategies of the resistive plate chambers of CMS to a more sustainable operation. So the compact Muon solenoid is a general purpose experiment placed in the LHC tunnel, and it consists in trajectography detectors in the innermost part, followed by a calorimetry detectors, then the superconducting solenoid, and in the outermost part of CMS, we have the Muon system. So the whole Muon system of CMS is built on gaseous detectors technologies, and the resistive plate chambers are placed in the barrel here in the orange box, and in the end caps in green here. So the RPCs are the blue detectors here. So they are the only gaseous detector technology placed in both barrel and end cap. So this is the CMS detector for run 3. And this is the CMS for the high Lumi period starting 2030. So despite the existing RPC detectors in blue, we are installing new IRPCs. They are improved RPC chambers in the forward region of CMS, where we expect a background in the order of 600 Hertz per square centimeter. So RPCs, they are made of parallel plate chambers, as the name says. So we have an uniform high electric field in medium where we have a gas. So when the particle passes through it, it will ionize the gas, and the high voltage will make it produce an avalanche. And then we place the strips outside this gas gap to measure the induced current by the avalanche. So in CMS, we use always in all part of CMS the double gap RPC chambers with the strips placed in the middle. So differently from the cylindrical gaseous detectors, as in the RPCs we have uniform high electric field, we have better timing resolution. So that's why we have RPC in all CMS systems. So it's helping the other gaseous detectors in terms of timing. And in the RPCs, we use a standard gas mixture. As Shana said in the plenary yesterday, it's a kind of golden mixture. It works very, very well. And we don't know exactly why, but it's a golden mixture, really. The problem is that more than 95% of it is made of tetafluorethane, and we have also a small percentage of SF6. Even if it's in a small percentage, its impact is very high, as I'm going to show. So, given the new policies, as we have been discussing in this conference, we should decrease the emissions of the greenhouse gases. And at CERN, we have a very high impact by the direct emission of these gases from the detectors. And it's also, of course, it has also an impact in our pockets because the tetafluorethane is getting very expensive in the last years. So the idea today is to present how we are addressing the CERN F-gases policies inside the CMS RPC project, promoting R&D on alternative gases, reducing leaks, training personnel, and also in the monitoring, managing, and recuperating and recycling the gas we use. So these are the four different strategies that we are employing inside our community. So the first two strategies, they are related to gas recirculation and recuperation. So as I show here, in the gas recirculation system, we take the mixture from the detector and we simply reinject it back there. We do it with 90% of our gas since the beginning of LHC operation. And the problem is that it will reinject also the impurities in the mixture of the mixture due to the irradiation it will receive when it's inside the detector. And we have the recuperation system. Since July 2023, it's operational with 80% of efficiency. And instead of simply reinjecting the full mixture back to the detector, we have a gas separation and recuperation, and we simply reinject the pure and the recuperated molecules of freon and back to the system. So a third strategy is on the gas leak. And something is very important is to thank the EPDT group of CERN. They are the responsible of taking care of recirculation and recuperation system. So a third strategy is on the leak repair, because if the gas in these loops here, if you have a leak in the detector level, you cannot recirculate nor recuperate because the gas will be released in the atmosphere. So we had a problem affecting only the barrel chambers in CMS, which are the half of the chambers we have. And it was because we had a bad batch of pipes. Because, I mean, the technical specification of the pipes are the very same for end cap and barrel chambers. But then in the barrel, we have this problem because the polyethylene became brittle on time due to the irradiation. And then it starts to crack and we start to have leaks. So since 2018, we agreed with CMS that we would disconnect leaky chambers because the trigger system in the Muon system of CMS is redundant. So when we turn off a chamber, it doesn't mean a hole in the detector. We still have the other chambers capable to measure the Muon when the Muon passes through this region. So if a chamber has more than 10 liters per hour of leak, we disconnect it. In LS2, long shutdown 2, we performed a massive repair of leaks, but at that time we had a procedure where we repaired the chamber locally, punctually at the source of the leak. The problem is that the leak was reappearing somewhere else. So in some cases that we repaired the NS2, we had leaks again. So since 2023, we developed a more robust procedure that is permanent so far. So all the 10 chambers we have repaired since 2023, they are still leak tight. So they are compatible with 0 liters per hour of leak. And then we do it by completely restoring the gas pipe. So we take out the connections from the gaps and we put a new V0 blue pipe as the one you can see here in this picture. But in order to do it, we have to fully extract the chambers. And in the barrel, the RPC chambers, they are attached to the drift tube chambers, another gases detector technology placed in the barrel of CMS. So that's a lot of work, but it works. But I mean, it's functional. So the fourth strategy is on the alternative gases for the greenhouse gases reduction. So in one side, we have more, let's say, permanent, a trial, of course, but in a more permanent way, so a long-term solution is to completely replace the tetrafluorethane by an alternative. And here I will bring you some results on HFO, which is an isomer of the C3H2F4. And it's the strategy that the industry used to replace the tetrafluorethane. But then I will show you also the problematic we have with this replacement. So another solution which can be treated as a midterm solution is to partially replace the tetrafluorethane by CO2, which is inert gas, priceless. I mean, it's very cheap and has a lower impact for the environment. And this is the strategy adopted by Atlas since 2023. They injected 30% of CO2 in the mixture. So, and the good thing here is that we decrease the working point with this addition, but our recuperation system is not compatible yet with this molecule. So that's why we are not going through it right now. So here in more details, the summary on the global warming potential of the mixture when we have the ECO2 and ECO3 mixtures, which we test with EcoGas collaboration. And I know that tomorrow they will have also a talk here with more details on that, and other CO2-based mixtures in a collaboration with the Atlas team and EPDT group. So we do our testing GIF, gamma irradiation facility, which combines a high irradiation from a season with beams in the periods we call test beams. So we can place detectors inside the bunker and measure the muon, the efficiency of the detector on reconstructing the muons under a high gamma background, as we will have in the high Lumi. So here a bit on the detector setup, we have a detector prototype. It's we use the same gaps or the same gap material from the IRPCs, but this is a prototype. We don't have the final electronics here. We use electronics prototype because at that moment we were still in the beginning of mass production. And in GIF, we also do the longevity study. So we keep the chamber on and we measure the current and efficiency over time. So to evaluate how the different gas mixtures, they impact in the chambers in a long-term operation, because the chambers, they are replaced in CMS for 20 years, and the ones which are there for 15 years, they will stay 20 years more. So it's not just to replace the gas mixture. We have to evaluate how the chamber will behave, how the gap will behave, and how the material will behave. So here are some results with the HFO-based mixtures. So we see that all HFO-based mixtures, they have higher working point, because this plot here, it's just we vary the high voltage in the gap and we measure the efficiency. That's how we take first the working point, which is the high voltage the detector will operate, and also the efficiency. So here we see that the plateau is around the almost 100%, but the working point is higher for green and blue mixture, which are the HFO-based mixture. And the same happens when we have source off, which means no gamma, or sorry, or with radiation. I promise I'm almost done. And here's the results in terms of current, where we see 40% more current for the HFO-based mixtures in comparison with the standard one, and also more mean gamma cluster charge for this eco mixture. So this has to be evaluated in longevity tests. And up to now, we have integrated only 4% of the high Lumi expected charge. So here for the CO2-based mixtures, we see here 1 to 2% drop in efficiency with 800 hertz per square centimeter, which is a bit more than what we expect for high Lumi for the different mixture that we test, and a drop in efficiency that becomes greater when we have more after the irradiation. But we think that now actually we are sure that this is only due to this prototype electronics we are using, because we see the same drop for all the mixture. So here in terms of current, we have 20% more current for CO2-based mixtures with respect to the standard one, would also means that we have to keep going in the irradiation tests. So as a summary, as I said, the replacement of the standard gas mixture in the CMS RPC is a very complex and non-trivial challenge. We have several strategies in order to mitigate the environmental impact of our system, and we managed to cope with the target at the end of run 3. So we emitted 28% less with respect to 2018. This was our target, and we did it. And regarding the alternative gas mixtures, as I said, still some R&D is needed. So we don't foresee the change of the standard gas mixture in the near future. And that's all. I'm open to questions.
Thank you very much, Joao. Are there any questions? Okay. Yes, Christine?
Maybe just a very brief one, because I'm terrible with numbers in my head, but the 20% lower emissions that you quote, is this within the targets that CERN was aiming for? So basically CMS is doing their bit?
Exactly. So if I come back here, we had this target to have a 28% reduction by the end of run 3 with respect to 2018. This, unfortunately, is not, it's old. But yes, I mean, run 3 finished yesterday, not yesterday, but a few weeks ago. But the good thing is that, yes, we managed to cope with the target.
So 20 versus 28%, I guess.
Exactly.
Okay, thank you.
You're welcome.
Thanks. I had actually the same question, so I'm glad. Okay, so that means that the trend looks good after 2024 for the next CERN environmental report. Then we are going towards
Exactly.
Okay, very good.
Exactly.
So thank you, Joao.
Thank you, Ian. Thanks, everybody.
You're welcome. And we will move to the last talk of this session from Dimitra Spathara.
Hello.
On materials for our detectors.
Yes. Can I share my slides? First, can you see my slides?
Yes, not yet on full screen.
Okay. Full screen? No?
Yes, all good. Please go ahead.
Great. Thank you very much for inviting me to discuss about my work here. Do you see the full screen, or is it?
Yes, it's all good. Yeah.
Okay, cool. Sorry. Go back. Okay. So I'm a material scientist, so I'm not a particle physicist, but I work with particle physicists. So I'm based in the University of Birmingham, And today I would like to talk about designing materials for dark matter search, rare event searches, dark matter events, and other rare events. So in particular, copper-based alloys. You can see here in the picture some really nice, beautiful copper crystals that have been fabricated through electroplating, and by my colleague here, Patrick Knights. And just briefly to discuss about the motivation of this work is the direct dark matter detection. So assuming that we are able to detect collisions between dark matter particles and target nucleus of our gas detectors or detectors with liquid, we will only see the nucleus that will recoil, and we will not be able to see the dark matter that particle that will scatter off. This recoil will create a signal in our detector, and so we are aiming to detect these signals in a gaseous detector like a SPC, the spherical proportional counter. We have a copper spherical cell which acts like a cathode, and we have an anode in the center. And once we get this recoil that will create our signal, we will have electrons that will be emitted by this ionization and will be attracted by the center of the detector by the anode. These rare events are actually very, very rare. So we try to suppress any other background that we get, any other interactions with different particles. So these experiments are taking place in deep underground laboratories, avoiding also cosmic rays and background from there. But also we try to reduce all the materials that will introduce background in our detections. So you can see here the spherical detector of 1.4 meters diameter that is now in Snow Lab and collects data. And this is made out of copper. And as you can see, we really aim for very radio-pure materials. Copper is the material of choice to achieve extreme radio-purity levels. It is electrically conductive, which is works very nice for the detector of unity experiment. It's strong enough to be low-pressure gas vessels. It has no long-lived isotopes, and it's commercially available at high purity and low cost. However, backgrounds can be introduced. First, in cosmic ionizing background, we get reactions of copper with neutrons, and we can get cobalt-60, which has a half-lifetime of 5.3 years. And also during manufacturing, we get contamination through thorium and uranium decay chains. And if we see, for example, the uranium decay chain, we measure for 4N commercial copper a very nice level of radioactivity, very good radioactivity, low radioactivity levels. But when we indirectly detect lead-210 much higher levels, we understand that the circular equilibrium has been broken, and usually the suspect is radium-222, which is a gas at standard conditions and sits on surfaces, and it's around in the atmosphere. So during not only like these decay chains are actually more can introduce more background during the decay. Lead-210 is very difficult to get rid of because its half-lifetime is 22 years. So there are some challenges. But however, we choose a different type of fabrication of copper to mitigate these challenges by introducing the electroplating and electroforming. In this way, we make use of copper high reduction potential, which we can tune in order to get in the cathode only copper electrodeposits and avoid all the uranium and thorium ions that stay inside the bath. This fabrication method has been very well understood in industry. However, in order to optimize the method, they use additives which are mainly lead-based. This is forbidden for our case, so we choose to do this electroforming additive-free. And this is, of course, very challenging because without additives, we have dendrite formation and some different oxidation, some other different challenges on the surface finish. So we choose to have a pulse reverse plating and a lot of different work around it in order also to scale up from a very small scale to large scale of the size of our detectors. The way we introduce this manufacturing process can lead to benefits for a range of different experiments. And also, it's through the years, it's a proven fabrication method. We have the example of Majorana demonstrator, which you understand that from different places of the detector, there were very, very low backgrounds in thorium and uranium, less than 1 part per trillion for each of the different samples that they were studied. So the statistics are really good. And also in UC electroform coating, we had this demonstration when we electroplated deposited copper through this method on commercial copper. We found that we can suppress the background from the commercial copper. So this electroform copper acted as a buffer. So we don't get this alpha, beta, gamma particles in contact with the gas inside our detector. Of course, this method takes a lot of time, and we can get like this spherical coating in about 6 months. Enough to run our experiment, but this also demonstrated that we can also get a fully electroformed copper spherical detector, which is something that we are now working on. But what is the motivation to have a copper-based alloy? Of course, if you think about the rare event searches, in order to maximize the physics potential, we would need much larger scale of these detectors, or even the ability to have the gases at the higher pressures in order to multiply the statistics of collisions between dark matter particles and the targets, the targeted gas. So there were some preliminary attempts by colleagues in Pacific Northwest National Lab to synthesize this both in 2018 and 2021 by electroplating copper on chromium and chromium on copper in order to make an alloy between copper and chromium. colleagues realized that it's very difficult to incorporate chromium inside copper even after heat treatments at high temperatures. And also the aiming of a second heat treatment was to make an alloy stronger than copper, so it will be mechanical enhanced, and we also get the electrical conductivity of copper at a very high level. In the second attempt, there were 3 different temperatures, and also aging the second thermal processing was attempted at a different temperature, but both times at 12 hours. We can see from point measurements that they have achieved some. They have some indication of hardness at a better level than electrophone copper, and also with the electroplating. Even though with chromium electroplating, we understand that we get some contamination with uranium because it's not the same potential that works for chromium compared to electrophone copper. However, since we are not able to incorporate a lot of chromium, the projection of the radio purity tells us that it won't compromise the radio purity levels. So I don't have much time, but I just wanted to introduce a little bit about the idea of using computational thermodynamics in designing this material. And we found from these papers that are included in the abstract and here in this work, that we are able to use thermodynamic properties and kinetic properties of different species inside the alloy, and predict as well the properties, and also design the layer configuration in the first stage of electroplating. I'm really sorry that I cannot really go into much details, but we were able to validate simulations with experimental data from previous attempts from the colleagues in PNNL, and we found that we can have solution homogenized alloys at practical times, but also optimize the aging process from 12 hours to less than 2 hours, possibly also in 1 hour, and maybe also at lower temperatures at 500 degrees Celsius. So we avoid the trial and error approach. We are able to predict also properties like the total strengthening that we can get from thermal processing. And we're also able to optimize the parameters and effectively get the manufacturing conditions in order to have an effective material that could replace in the future copper and maximize the physics potential. Also here in this paper, we discuss the 2 different case studies of how we are able to do this with dark sphere project or the XLZT future next generation relevant searches experiment. And with that, I can discuss this further with questions. Thank you for listening.
Thank you, Dimitra. So I just have a quick question. Maybe that was on your next to last slide, possibly. Would there be potential applications outside of high energy physics for that type of procedure, like in industry or whatever?
Yes, so copper, high strength copper alloys, not the radio pure part, but just the strength and the electrical conductivity of copper is really important for applications in electronic circuits. Also, high-speed rail cables. They are trying this with different, with also chromium and titanium species. I didn't have the time to for this, but they don't, since they don't care about the radio purity, they start with casting or arc melting, and they prepare these samples. And so like the whole CalFAD tool, the calculation phase diagram method, the framework that I'm using, draws the properties in these databases, thermodynamic and kinetic databases that we need for running our simulations from these particular samples. And so what I'm going to do next is to develop more accurate descriptions of these properties for copper, chromium, and titanium, and how they interact together. So we get a better description and prediction also for our application, but possibly in the future also for some applications that they will start caring also for radio pure materials, that they wouldn't. They would like to eliminate the impurities that you can incorporate from different manufacturing processes.
Okay, thank you very much. So we will take a short break before we get to the panel session. But before that, don't leave right away for your coffee. We would like to take a picture of the attendees. So if you don't mind switching on your camera for a few seconds, or if you have a preferred picture, whatever. And this way we'll hopefully get everybody. I guess we'll take a few just to be on the safe side. And yeah, especially when my mouse doesn't move anymore.
Are you saying cheese?
Oh, if you want to say cheese, go ahead. Ready, everybody? Yeah, we'll take the best one afterwards once we have most of those pictures on. Okay, hopefully we got everybody. Thank you, everyone. So we will reconvene in 10 minutes, and we'll have this great panel discussion about moving out of computing and high energy physics towards sustainability with our 5 panelists. So see you shortly. And we will pause the recording during the break. If you want to interact, feel free. It's not recorded anymore.